Now that we've accomplished this for a single first order differential equation, meaning this equation, what do we do for multiple? Throughout our course, we're interested mostly in this equation. And you can put a forcing function over here. So how do we solve this using Euler or likewise ODE45? Well, let's first rewrite this equation into the standard form that we're used to, and that form is x double dot plus 2 zeta omega n x dot plus omega n squared x equals to some forcing function. And I tried to do a decent job making the zeta. Well, before we do that, we could basically look at this as if it was a velocity. V dot plus 2 zeta omega n v plus omega n squared x equals to f of t. If you stare at this, what you see is one equation, but you also see that there is another one, mainly x dot would be v. You could rewrite this in this particular order. You can write it in the other order as well. F of t minus 2 zeta omega n v minus omega n squared x. Now, if we look at this real close, we may be able to turn it into a vectored form of an equation, namely one that looks like this. I'll make enough room, not knowing which one, then plus anything that doesn't have a v or an x in it, which would mainly be function in time and 0. Okay, the top equation is pretty simple. It's that. The bottom equation you have to be real meticulous about. Omega n squared minus 2 zeta omega n. So if this was rewritten as just a vector, say z dot, where this is a vector is equal to a coefficient matrix times z plus some forcing vector, where in fact this is your c, this is your forcing function, this is the z, and like before we were talking about, Now let's formalize this in an interesting way and make it even more general. We're going to basically be trying to solve this at some point. We also have this equation. We have Euler sitting in here. Let's now formalize this, and let's call this, we'll do a copy, new, paste. I'm going to call it Euler V for a vector. I'm going to go ahead and save it. However, everything now is a vector. T-span still remains the same. This remains the same, and we're going to require that we have equally spaced points in time. We are going to now have what I'm going to now call xv0. And I'm going to change this to a capital X. Change this to a capital X, so we'll start working on this in a little bit. Here's what else we're going to find. I have an x2, which will be pulling the first component out of here and the second component out of here. Now, maybe I should do this first, is start working on the first order differential equation and change that. Let's change that. Copy, new, paste. Before I do, I'm going to do something like this. Global. I'm going to do omega n, zeta. Now these are coming straight from the omega n right here and the zeta. There is no real other term that I particularly need at the moment. Now, what I've got is something slightly different. I'm going to call this a Z now. Call this a Z. The way I'm going to call this, I'm going to create this matrix. When I say this matrix, I'm talking about this one. Slide it to the other screen so I can look at it off screen while I'm typing it. And I'll call it just a capital C equals to 0, 1 minus omega n squared minus 2 times zeta times omega n. I'll go ahead and put a forcing function on there for the sake of it. Argument 0, and then sine of 4 times time, for lack of anything better to do. Now, my dz dt is equal to nothing more than c times z plus f. And that's it. Now, I need to really change this to second order differential equation. Then I'm going to run back over to Euler testing. But when I do, I'm going to go ahead and save this. I'm going to work on it later. Right now I'm going to focus on ODE. So I'm going to go ahead and basically comment those two lines out. Change this to second order. Now I need x and v. So actually, here's what I'm going to do. I'm going to try to go back and reclaim that for the first order so that I can keep those intact. Okay, once I'm intact, I'm working on the second order one. One of the things I have to do on the second order is I have to realize that I need to input those. So I need a global there, but I also need to define those, making n is equal to, say, 5. And then let's say zeta is equal to 0.95. So this should be a underdamped system. I'm going to go ahead and look at t-span. T-span, I'm going to go from 0.1 seconds to 8 seconds, for example. I don't know why. XV not. This is the initial. I'm going to say 3 and 5. Now, if everything goes right, we should be fine. It's kind of a misnaming here. I've called it Euler testing, but I'm basically focusing on ODE. I'm going to basically put a breakpoint there, and I'm going to go ahead and run this. Okay, so value of the local variable doesn't match a change in globe. Okay, so at this point, omega, there's your zeta, here's your time, there's your z. Okay, so let's step through here. Here's your matrix C. There's your forcing function. Since time is 0. Alright, mistake. Let's go ahead and put a breakpoint there, rerun it, decipher our mistakes. A C, Z. If you want to know whether that was the problem, right click, evaluate the selection. Seems to be okay. F, aha, it is not listed correctly. Let's do it like that. Here's the advantage of MATLAB so many times. I can evaluate the selection. Now I should be able to say this and it'd be evaluatable. Yes, so need to quit it, save it, go back to it. Now I can hit the F10 key and it goes on. Should be able to hit the F5 and it'll return at this particular time that value. And you can see the value of time changing. If you want to see it better, you can look over right here. I'll just start hitting the F5 over and over. And what you find out is the time value here is increasing. Then if you just get tired of that, you can go on back to here and hit a continue. Obviously we have an error here, and the error stems from a simple case in which we need to identify something. You have x1 which has 2 values. Now notice we started with xv not being 3 and 5, and you notice that it's 3 and 5 at the top of this matrix here. The way I had these equations set up is the first equation was the x. Second equation was the v, velocity. So the first column will be x, and therefore if you want to plot the position, you need to plot that, and I no longer have an x that I know of, although the x is hanging around from before. Let's take that out. Now if I quit debugging and run it again, I should be able to step twice, and you see a solution here. Now I can also change it. Let's back off on, tell you what, let's embed that into our docket in right here, and let's observe what happens if we start changing our damping. For that matter, take off all the breakpoints, quit the debugging, run it. So reducing the damping ends up with something interesting, something you would expect. Coming up against the high damping, you can see we're getting pretty close to a zeta of 1. When you get a zeta of 1, this is what you see. When you get a little zeta a little bit higher, you pretty much see that it technically doesn't oscillate anymore, and you could run it to something ridiculous and it would be fairly slow to return to its steady value. Now what we've done here is we've built the ability to solve a general form, and actually I tell you what, let's do 0 times this. The forcing function will take it out of play, so let's run that again, and what you see is that, okay, so this is a forced solution here. Okay, now at this particular point it's no longer forced. One of the things you'll see, let's go ahead and increase that. If you take this plot and zoom it, what you see here is the initial displacement of 3 like we specified, and the initial slope here, the rise over the run, should be 5. Now if you want to do phase plots, let's do a phase plot. I don't think this will work. I believe it's going to give me an error, but I'm going to try it anyway. It didn't give me an error, but it certainly didn't give me what I wanted. So what I really want is I want this. I want to plot the velocity on the x-axis, the position on the other axis. So what you see is a velocity and a position. What you initially saw was 3 and 5. So let's go ahead and let's look at this in two forms. First form, you ended up right here at 0, meaning 0 position, 0 velocity. If I draw it on out and put a point 1, you'll see a spiral occurring. This spiral is because, mistake here. There wasn't anything wrong with what I did. It's just that it plot the displacement. Okay, so this is the solution of the position. So what you see is it damps out. So what you're seeing is the initial position gets started up here at 3 and 5, and you see it's oscillating back and forth as it came around back to where it initially ended up. It's making the cycles. It hasn't damped completely out, but I can get it to damp all the way out by doing that, and you'll see it'll damp all the way out. Should eventually. If you really want it to damp out a little faster, you can put a 0.5 there. You can watch how the spiral takes place. The spiral goes very quick. Okay, now this is still with the 0 times that, so I'm thinking I still am getting, and let me double check that. Forcing function is 0, continue several times. I'm still getting a forcing function of 0. That's because 0 times sine. So you have a lot of flexibility here. You can put a forcing function in here and do all the different types. This would self-contain it so that you could do all the different types of damping and all the different types of forcing functions. So how do we accomplish this in Euler? Now, it may seem like it's a foolish thing to do, but it's really not. Let's go ahead, because we get a feel of how ODE45 is working by looking in at Euler. So here's our Euler vectored. So what we're going to do, I'm going to go back to this. I'm going to do a copy. I'm not going to go to 80. I'm going to go to 10. And I'm going to go ahead and pick out a 0.2. I'm going to go ahead and do a copy and then a paste. But this time I'm going to call Euler vectored. You can pretty much rest assured that it's not going to work the first time through, especially since I hadn't fixed it all the way. But we are going to stomp it around in here. We go back to Euler testing and run it. Hit F10 and we end up right in here. We have the ODE function, T-span, our initial conditions. So the first thing that's going to happen is if I highlight this, right click and evaluate the selection, it's not going to like that. So let's say I put it in as a capital because that's what I'm putting back here. If I put that in, what am I sending here? I'm sending only 3, when in actuality I should be sending 3 and 5. So what is that? That is the first row. Is this the value I should send? No. What about this value? Yes. Now the time value is fine. It should be okay. So I've already made a mistake, and if you notice I saved it. It has to start over. So we're going to go back and run it again. We end up back here. This time I should be able to hit F10. Then I'm going to hit F11. I see that I ended up in here. One of the things that's not very nice here is that I haven't ended up with the correct formation. You'll see what I mean in a second. If I'm trying to multiply this times that, it's going to tell me matrix dimensions must agree. So as a result, it is required that I send this in as a transpose. So we'll save it again. Euler testing. Okay, now hit F10, F11. You see it came in the correct way. There's our C matrix. There's our F, which doesn't have anything. It's a 2 by 2 times a 2 by 1 and a 2 by 1, and I'm okay. I come back out of the routine. I have that. Now that times this, and the problem is I need to represent this as an X, and this as an X. Now here's what I do a lot of times is I'll highlight, see if I evaluate that selections. No, it doesn't work. Why does it not work? Let's take a look. Evaluate that. Aha, needs to be transposed. Let's take a look at that now. Right click, evaluate the selection. Yep, looks good. Right click, evaluate the selection. I still have the 3 and the 5, but the next time step gives me that, and I'm incrementing the time steps. Okay, seems like I'm okay. I'm feeling lucky, so I'm going to hit that and then hit a F10. I get a solution. Hey, looks nice. There's my phase plot. There's my new phase plot. Now what I'd like to do is I would like to compare the two of them. So what I'm going to do a plot and a hold on. Go down and do this plot, do a hold on. And I'm going to basically save it and rerun it. I'm going to jump through here. Okay, so there's my figure 1. That's not ODE anymore. This is Euler. Yeah. I'm not sure if it holds that entity on there, but we're going to find out. So I'm going to just take the legend off right now. Run it again. Jump to the next. There's my Euler solution, which it still looks like I put that on there. Do a F10. Plot again. What you notice is they're not exactly right. I think I'll change this color to red so I can see the difference. Save it, rerun it. So you see, whoop. Hey, what? I'm thinking I'm loading this picture up, so I'm going to do a clear figure and a clear figure. Save it, run it again. Ah, there we go. So what I'm getting is an Euler which doesn't necessarily match up with the ODE 4.5. Let's see how the phase plot operates. And I think I want to put it on there as red as well. And then I think I'm going to go ahead and copy this, put it right here. So I'm going to save it and run it again. See, so it's considerably looking different there. It starts at the same spot, way out of sync with the other one. So here's what I'm going to do. I'm going to take my T-span, I'm going to do a copy, put it right down here in front of the Euler. Yeah, I'm going to go ahead and keep it that way. Okay, then I'm going to do this, run it with a higher resolution, what you find out, or what you should find out. Go ahead and take that off and continue it all the way through. What you find is that they do converge to each other, and that should give you a comforting feeling that if I use a small enough time step that I can essentially, now see here it's going to take some time to run. You can see it's busy still. But it did do a little bit of ridiculousness there. And so what you see, the difference between these two is almost undistinguishable. You might find a little bit of difference, but you really have to search very, very hard to find it. But if you were trying to be quick and get a solution, you'll see the first thing that happens. If you go too far, notice what happens with the Euler. The Euler solution diverges or becomes completely out of control. You can do it several times. It has lost stability is what it has done. It is no longer a stable solution. Now it is stable. You notice Euler does damp out, but it's completely inaccurate. As you shrink the time step down, you'll notice it becomes a little bit more accurate, and then eventually you end up with something like this. So what I'm saying is that delta t, so we accomplished what we were setting out to do, and I'm going to call this lecture done.